Hi, my name is me. We're Team 10 and 15 from the University of Florida, and I'm here along with my teammates, Dung and Dot. Our advisors are Tracy, Stepien, and Youngmin Park. In this project, we built a mathematical model to explain how animals and mixed species detect predators better by coordinating their vigilance. We were inspired by studies showing that diverse groups, not just big ones, help animals spot dangers more effectively. Our goal was to turn this idea into a probabilities model, linking group size, coordination, and diversity into predator detection. This leads us to why group vigilance equals modeling mathematically. In nature, many prey animal group together stay safe and spot predators faster. When one detects danger, others react right away. This is called information sharing. In mixed species group, this works even better because each species has unique senses. One may see well, another may hear or smell better. But grouping also has downsides. If animals rely too much on others or stand at the same time, there can be moments when no one's watching. A model explores this balance, how group size, diversity, and synchronization affect how well predators are detected. To explore that, we first define the main variable and assumption behind our models. We use six key parameters: N is group size, VO is the baseline vigilance for a single animal, K is how quickly vigilance drops as the group gets larger, S is the synchronization level, mu is the detection rate constant, and T is the time window we observe. We assume that all species have similarity, so we can focus on group effects, not species differences. Animals are partly synchronized, not completely independent, but not perfectly aligned either. Detection follows the poison process, meaning the chance of spotting a predator depends on total vigilance over time. This assumption keeps the model simple but realistic. Now that we have set the parameters, Zoom will explain how we built up four models describing vigilance, independence, and detection probability.
The first step is modeling how vigilance changes for a single individual as the group grows. We define individual vigilance as shown in the formula. This function means that as group size n increases, each individual spends less time scanning because the risk is shared. The parameter k controls how quickly vigilance drops, and the higher k means individuals relax faster. The denominator ensures vigilance always remains within 0 and 1. As shown on the right, V decreases smoothly with group size, and this curve forms the behavioral base for the next stages of our model. But group members don't act completely independently. That's where our second model comes in. In Model 2, we quantify how synchronization affects the group's overall coverage. Even if there are many animals, not at all act as independent observers. When the scanning behavior overlaps, the group effectively has fewer independent watchers. We define this relationship as an effective. When S equals 0, everyone scans independently, so an effective just equals N. When S equals 1, the group is fully synchronized, which means that they all act as one. This captures correlated vigilance seen in nature, where some coordination helps but too much reduces coverage. On the right, you can see that as synchronization increases, the number of effective watchers drops significantly. Once we know how many independent watchers a group effectively has, we can combine this with individual vigilance to estimate overall group awareness. In Model 3, we calculate the probability that at least one member of the group is vigilant at a given time. This is expressed as C. Here, 1 minus Vn to the power of n effective is the probability that all effective watchers are inattentive at once. And subtracting that from 1 gives the probability that at least one is watching. As shown in the graph, C rises quickly with group size but level off, meaning the benefit of adding more members diminishes. When S is small, the group maintains strong coverage, but as S grows, overlapping vigilance reduces overall group awareness. This function is crucial because it links individual behavior to collective advantage. Finally, we extend this into a dynamic process, how likely the group is to actually detect a predator over time. Our final model connects vigilance to actual detection events using a Poisson process. The probability that the predator is detected within time t is p. This means detections increases with both vigilance and time, but it approaches a maximum limit near 1. As shown in the plot, detection probability improves rapidly with group size, but then plateaus, again showing diminishing returns. Groups with higher synchronization or faster relaxation detect less efficiently because fewer members are watching independently. Together, these four models show how vigilant independence and timing interact to shape group detection performance. With this model complete, that will now walk through our key outcomes, what they imply for real animal groups, and potential direction for improving this framework.
Hey guys, I'm Dat. So our simulations help us answer the main biological questions. First, mixed species groups are indeed more likely to detect predators, but only when their scanning is not perfectly synchronized mathematically when S is less than 1. Second, the effect of group size is positive but saturating. The greatest improvement occurs in moderate group sizes before benefits level off. Third, the model predicts that groups of around 3 to 5 species gain the strongest advantage. Beyond that, additional species contribute very little, as overlapping vigilance causes diminishing returns. Finally, we observe an upper bound on benefit. Once synchronization dominates, adding more individuals no longer increases detection. Overall, these findings match ecological observations. Diversity and moderate coordination provide the best vigilance outcomes. However, this model is intentionally simplified. Let's look at its main limitations and how we could expand it. Our current model assumes all species share the same detection rate and that group size stays constant. In reality, species differ in their sensory abilities and groups change composition as animals generally. We also don't account for communication, movement, or predator dynamics. Future versions could introduce species-specific detection rates to simulate how sensory diversity affects group performance. It could also add predator speed or approach direction and model spatial heterogeneity to reflect real interactions. These additions would make the model more realistic and applicable to ecological data or even AI simulations of collective behavior. Our framework is supported by prior behavioral studies that inspired these modeling assumptions. So here are our citations. Thank you. In summary, our model shows that moderate synchronization and species diversity leads to the best predator detection outcomes. Too much coordination reduces independence, while small diverse groups balance awareness and efficiency. This framework bridges ecological behavior and mathematics to explain how collective vigilance emerges naturally. Thank you for listening. We'd be happy to take any questions.